Okay. Uh, okay, and we want to understand if how good is G going to generalize from training data to test data. We generate G by training a certain hypothesis class, and then we want to see if G looks good on the training data set, will it continue to do well on the test data? That's the central question we are interested in. So when we are measuring the loss using squared error and when we are considering regression problems, then it turns out that the VC theory that we discussed last lecture is not that useful. We should use a different approach called Bias-Variance Tradeoff in order to understand the performance of G. So to do that, we'll make one change in notation. Instead of just writing G, we'll add a superscript D to it, which means that this G is generated using this training data set D. As we change our training data, as we change the set of examples we have, we could get a slightly different hypothesis. And we want to make the notation explicit and say that this G is produced from this training data set D. So for our discussion, the data set D is random. Previously, we assumed that all the examples x1 to xn are generated IID, independent, identically distributed from some distribution. But today, we will just assume that D, the data set D, is drawn from some distribution P of D. So there is some random mechanism from which our training data is drawn. Previously, we were making a stronger assumption. We were saying that each data point here, x1, x2 to xn, is drawn IID, right? So we don't need to go in that much detail in this analysis. We just assume that there is some distribution on D. So D is random. Once we feed D into our learning algorithm, we get an output hypothesis G, which is also random because D is random. And this denotes the dependence of the output hypothesis on the training set. So that's what we want to, that's the notation we want to use right now. Now, what we will do is we will define a new concept called average hypothesis. So imagine that you perform this training not once, but over a course of several weeks. So imagine in the first week you have a few patients coming in, you want to collect data, it's some medical application, and then you get their data, you run it through the algorithm, and you get one output hypothesis. The following week you get a new set of patients, so you have a new data set, D2 say, you run it through the algorithm, you get a second hypothesis. And you do this over a period of several months. So let D1, D2, up to dk be k independent samples drawn from the distribution PD. So this could be the data you collect in the first week. This could be the data you collect in the second week and so on, independently of the first week. You take each DI, you pass it through your learning algorithm, and you get as output GDI. So you're not here combining the data from the first week, second week, third week, and so on. You're just independently training each model. So the output each week will be slightly different because the data set is different, right? And what you do is you try to average out the DIs. You take the average of the output hypothesis that you get across all the K data sets. Okay, so what you do is you define G bar of X, the output hypothesis, to be 1 over K summation of K going from 1 to K GDI of X. So this is the average across the outputs in each of the K data sets. And you do this as K goes to infinity. So you take a large number of such copies and train it. So as K goes to infinity, this will converge to the expected value over D of GD of X. So this is a quantity we have never discussed before. This is a quantity where we are saying that our output hypothesis depends on the training set. So let's average out over all possible realizations of the training set and now see what the output hypothesis will look like. So to understand this, let me do a simple example and then I think it will become clearer what we are trying to compute. So let's say our unknown function that we want to estimate is sine of pi x. So x is the input variable, scalar here, so we are in one dimension. Our label y is obtained by just taking sine of pi x. Okay? And we'll assume that x, for simplicity, is between -1 to 1. So what you have is the following. The input data point x can be anywhere between -1 and 1. What you get is this output. This is f of x. It's sine of pi x. So when x is 0, f of x is 0. When x is 1, f of x is 0 as well. At x equals half, it is maximum, and so on. Okay, this is the ground truth. So any x I give you, you will get a corresponding y generated by this function. Okay? Now, of course, you don't have this function, otherwise there was nothing to learn. We will assume that you only get one sample. So your data set D consists of only one sample. So it consists of a point u comma v. So n is 1 here. We'll assume u is sampled uniformly from -1 to 1. So u is a point generated between the interval -1 to 1 uniformly at random. That's how our data sample is generated. And v will be f of u. So it is sine of pi u. So if u is, for example, a point here, this is u, the v that we get will be this value. If u is here, the v that we get will be this value, and so on. Okay? So you get only one sample. Things can get simpler than that. Just have one sample. The hypothesis set will be constant functions. So our output h of x will be of the form h of x is constant. It has to be a straight line. Consider the simplest possible hypothesis, just a straight line. Right? That's all we want to do. We are not even linear is even more complex than a straight constant line, right? This is the absolute simplest hypothesis class you can get. So if you get a point u v, what will your output be? If you get this particular u and this v, what should your output hypothesis be? What should g be? What constant line will the function you can draw is just a straight line. That's all you're allowed to draw. Now I'm giving you one point. Say u is here, it's 1/4, and v is sine of pi over 4, 1 by root 2, right? That's what you get. You get 1/4 and 1 by root 2. What should your output be? Should you output 0? Should you output this line, the horizontal line? Should you make h of x to be 0? Is that reasonable? What will you output? H of x is whatever v is, right? So the output will look like this. It should pass through v because you want to minimize your training error, right? That's a natural thing to do. Well, you have one point. All you know is this value here. You have no idea what f of x is. So your output will look like this. If you had a different value of u, say your u was here, so if you got this point here, this was the u and this was the v, your output hypothesis will look like this. If u was somewhere else, say this was the point you received, this was u and this was v, your output hypothesis will be this one. Okay, it's always a constant line that passes through v, because what will be the training error here? If this was the point and this is the line you draw, what would be the training error? It will be 0. You're perfectly fitting one point, right? Questions? Okay, so we are clear. The output g of x that we will produce, gu of x, just to emphasize that it is with respect to this input, will be sine of pi u. Or not sine of pi. It's just, let's write it as v. It is sine of pi u, but for simplicity, we'll write it as v. Okay. You get u comma v, then your output for this data set is v. Depending on what data you have, you will have a different output. It will be all straight lines. Any questions about this? Now, any ideas what g bar of x will be? What will be the average output in this case? Imagine you have like a lot of, like every time you get a point, you're drawing a line like this, right? Now, u is uniformly distributed between -1 and 1. So, your v will also be essentially uniformly distributed by symmetry. All lines are equally likely, right? And so when you take the average, you're taking the average over all these horizontal lines and it will get an average of 0. Okay. So in this example, g bar of x, the scalars I'm writing little x, is expected value of sine of pi u with respect to u. This is the output, and u is uniform between -1 and 1. And it's not hard to compute this expectation, and that is 0. So what is going on is that this is the ground truth. Your output hypothesis will look like a bunch of lines like this, right? Depending on which u you get, you will get one of these constant lines. When you take the average of this, which is what this expectation is doing, it's going to be 0. So that's an average hypothesis. There is another way to interpret this. This is the same quantity that you get if you had infinite amount of data. If you actually knew the ground truth, which is this function, and you had to find the best hypothesis in your class that approximates it. Imagine that you had infinite amount of data. So for every x on here, you know what f of x is. That's if you have infinite amount of data, right? So you essentially know what the ground truth is completely. But now you want to approximate this using a function in our hypothesis class. Now what is our hypothesis class? It's a constant. You can only draw constants because h is only a constant function. So you know f of x completely, but you can only approximate it by drawing a constant line, and you can change just where the value of constant is, right? What is the best approximation? You will have to set it right here. This will be your best approximation. So if you want to approximate the ground truth with an element in your hypothesis class, that is essentially what g bar of x is. It removes all the noise in your training data set because you're averaging over infinitely many data points. And then what you're left with is an element that is, in a sense, the best representation that you can get for f of x using your hypothesis class. That's the other interpretation. So output hypothesis with in H with infinite amount of training data. Okay. Or equivalently, it is the best approximation to the to f of x in H when f of x is known. These are equivalent statements. If I had infinite amount of training data, but I was restricted to just drawing constant lines, then this would be the output, g bar of x. Or equivalently, if I knew f of x, but I was only allowed to approximate it with a constant line, then I would still have to use this 0. So that's the intuition. Of course, g bar of x cannot be computed because you have only one training set with finite number of examples and you have to do your best output. So this is only a conceptual quantity, but it plays an important role in analysis. Any questions about g bar of x, what it is? So now that we have this, we'll define two quantities. One is the bias function. So the bias of x, when you have an input x, the bias that we produce is given by g bar of x minus f of x square. Okay. So intuitively, it is the difference, if you look at this particular definition of g bar, it is a difference between the ground truth and the best approximation you can have for the ground truth in our hypothesis class if we had infinite amount of training data. So this is something that cannot be avoided. If you're using a constant approximation to a sine function, you're going to have a large bias because this is the best approximation you have and you're far from the ground truth. So the bias is the difference between the best approximation in H and the ground truth. Take the difference at each x and square it. It's clear? So if you had a very complex hypothesis class which included sine of pi x, for example, then your bias will be 0 because that would be your best approximation to the ground truth. The other is the variance. The variance tells us, so the variance VAR of x, you take GD of x minus G bar of x. So the expectation of GD with respect to D is G bar. You take the difference between the random output for one data set, subtract the mean from it, take the square, and take the expectation with respect to D. So this tells you how much does each individual output fluctuate with respect to the mean. So if you go back to this figure, it tells you how much is the fluctuation. This is our G bar. This will be G bar. And it tells you how the spread is for each individual D. So what is the overall spread between the different individual outputs and the mean value? It's basically the definition of variance. But what you do is, the main thing is you fix it for each x. So you pick one value of x, say x is here, and you see how much the spread is, right? So we'll compute this for our example. Any questions before that? So in our example, f of x was sine of pi x and g bar of x was 0. This is what we showed. The average hypothesis, the best approximation is 0 all over. So bias of x was the difference between 2 square. That's sine square of pi x. So for any x, so if x is 0, the bias is 0. If x is half, the bias is 1 at that value. Sine square of pi over 2. So depending on x, the bias will be different because your approximation error is different, right? So at any, what is happening here is, this is g bar, this is f of x. You pick an x here, you look at the difference between the two, say it's delta, take square of delta. That's the bias at that point. And variance of x will be gd of x. For us, d is u, so gu of x minus g bar of x. Take the square and take the expectation with respect to u. And u here is uniform between -1 and 1. So this is the expected value of u of gu of x. Gu is sine of pi u. That's v for us. V is sine of pi u. G bar of x is 0, so we take the square of this. Okay, so our output is constant, right? So gu of x is v. So given any u, if this is the v, we are drawing a constant line. This is our gu. So it's constant, but the value of that constant is v. So that's why gu of x is v and v is sine of pi u. Okay, so this is independent of x. It's a constant function. Gu of x is always equal to v. Depending on what u is, it's going to be a different straight line. But when we compute the variance, we fix x and we take the expectation with respect to our data set. In this case, a data set consists of only one point, uv. So the randomness is with respect to u, and u is uniform between -1 and 1. Is clear? So any idea what this expectation will be? Anyone do this right away? So we can write the integral. So u is uniform between -1 and 1. So the density of u is 1/2 if u is between -1 and 1 and 0 otherwise, right? It's 1 over the length of the interval. So f of u looks like this. That's what the density function is. It's constant in the interval. So the integral is 1. The height is just 1 over the width of the interval. So we have to integrate this. Sine square pi u f of u du. Any idea what this integral is now? It's actually 1/2 if you do it. I'll let you finish it. Okay. So, all right. So, I believe it is true. Just some simple number, if it is not 1/2. Okay, so we have computed the variance. So what this is saying is, regardless of what x is, so regardless of where you select this x, if you look at the variance of the output, it's always 1/2. And the reason for that is that the function is everything is constant, right? So the spread does not depend on x. No matter which x you pick, you're just getting constant outputs. So the variance is independent of where you're looking at. It's not true for bias because f of x depends on x. But when you look at variance, you only look at the difference between your output and the average. You don't look at f of x. And since your outputs are constant, the variance is independent of x. Now, the third quantity is the average test error. Delta of x, and that is defined as GD of x minus f of x square, and then you take the expectation with respect to d. So this is actually the test error. GD of x is the output for that particular hypothesis when d is the data set we train over, right? You take the difference between GD and the ground truth, so that is your error at x, and you square it. And in delta of x, we take the expectation with respect to d for a fixed x. So what is going on here is that if you have, if this is f of x, okay, and your output, say this is the u that you get, and this is the v, so your output is this line. This is your output g. Now for any given x, if this is the x that you're interested in here, if this is the x that you're interested in, the delta of x will be the difference between f of x and g of x. So this is our estimate from the output hypothesis. This is the difference, and you take this gap, let's call this error, and you square it. This is what we are doing here. We're taking the output value, subtracting f of x, so it's this height, and you square it. So here we are using the ground truth value, the estimate, squaring it, and then we take the average. Because this is random, depends on d, and we want to know how good we do on average, we take the expectation with respect to d. So we do it for each line. Sometimes if u happens to be close to this point x, if you are somewhere here, then the gap will be very small. Or in other words, if your x was not at this point, but if your x was, say, somewhere here, then the gap E will be the error here will be very small between your f of x and the output. But if x was far away from you, the error will be large. So what you do here is you fix x, fix one particular point on this line, and then you look at the difference between GD of x and f of x, square it, and then take the expectation with respect to d. The average, no, because GD of, but that is for that particular V, right? So here what happens is, this is the U that we get. This was the U that we got here, right? Then V will be sine of pi U. So V will be this one point. Now my output is this constant. Okay, so I don't change. I'm not allowed to. My output has to be a constant function.
Taking the error across all values, is it?
And so for any, now I'm allowed to find an x. Now I'm allowed to give a test point. So this was training. Training is done. Training gives me this line, right? Now for test, I get a query point. So I get this x.
Okay,
and then I compute the difference. So x you can think of as a point you get during the test phase,
Okay.
and this is the output you get from the training, this is the ground truth. Okay? But then we are doing one more thing. We are taking the expectation with respect to d.
It's like, okay.
We want to understand on average, as we change d, as we draw different lines here, what is the test error going to be? So we fix x, we fix the query point during the test phase, and we change the training sets. That's how we have an expectation with respect to d. Okay? Everyone okay with this? So you will be doing quite a few examples on bias variance in next tutorial. So you'll be solving a lot of problems like this. So the point here is to understand the notation and the main ideas, and then you will get a lot of practice on this in the next tutorial. So what is GD of x? GD of x is equal to V. It's a constant, right? Which is sine of pi u. F of x is sine of pi x. Here x is fixed, so this function f sine of pi x is fixed now. The randomness is with respect to u, so this is equivalent to u. So if there are any questions, you should ask me now. We have defined three quantities. We have defined the bias function, which is up there. We have defined the variance function, and we have defined the average test error. There are three quantities we have defined.
So yeah, so just to make sure, so U is the training set while P is the test set.
U is the training set. V, so what the training point you get is U comma V. So U, so you get, U is uniformly drawn from this interval. Let's say U is this point. V is the label associated with U because we're doing regression, so we need label data, right? So U comma V is one point, one example. This is our X comma Y. But I don't want to confuse this X with the sample, so I'm using. So now X is the point you get during your test. So X is a new point you get during test. So we are fixing X here. I'm going to pick X here. And now I'm going to, so my test error will be my estimate minus the ground truth squared, okay, for that particular X. Now what I will do is, I will now, because the output is random with respect to D, here I'm going to take the expectation with respect to D, with respect to all possible choices of U. So if I had just one D, if I had only one example, this would be my test error. But now, normally if we had to compute the test error, we would fix D and take the expectation with respect to X. We would say my X can be anywhere here and it's uniformly at random. So I would take the expectation with respect to X in my usual definition of the test error. Here we are changing it and we are saying I'm fixing X, but I'm taking expectation with respect to my training data sets. Because depending on which training set I get, my output is different and I want to average out those effects. So what I have to compute is delta of X, which is expected value of U, sine pi U minus sine pi X square. Okay? Where X is fixed and U is the quantity that is uniform between -1 and 1. So I can expand that. I can just write this as a sine square of pi U plus sine square of pi X minus 2 sine pi X sine of pi U, expanding the square. So this is expected value over u sine square pi u plus expected value over u sine square pi x minus 2 expected value over u sine of pi x sine of pi u. I'm breaking up the expectation term by term. So what's the first quantity going to be? We computed this before, just on the previous page. It is the same as the variance, and it's half, I think. What about the second quantity? What is that? Sine square pi x, because this is a constant, it just comes out of the expectation. What about the third quantity? So I can write this as 2 sine pi x, which is a constant, times expected u of sine pi u, and this ends up being 0 by symmetry, because sine is a odd function and u is uniform. So this is half plus sine square pi x. Now if you recall our calculations, this is the variance function and this is the bias function. If you recall from previous page, sine square pi x was precisely the bias and half was precisely the variance. So what we have shown is that delta of x, at least in this example, is the variance plus the bias. So bias tells you how good an approximation you can do to the unknown function f if you know the ground truth, if you know f, but you are restricted in your hypothesis class. Variance tells you how much you fluctuate around the mean value. Depending on the data set you get, how much fluctuation you have. Okay? What this is saying is that the average test error, which is the quantity, the test error you will get at point x, is the sum of the variance plus bias. And in fact, this is actually true generally. This is not true for this specific example. In general, the test error can be decomposed as a sum of a bias plus the sum of the variance for that particular hypothesis. So this is a general identity. The test error, which is the difference between your output minus the ground truth square, right, on average, can be decomposed as the variance plus the bias. It's a very important property. So to understand this, we have defined two quantities. One is bias. How well can we approximate h, or how well can we approximate y equals f of x using hypothesis class H. This is what bias captures. How rich is our hypothesis class? If it is very rich, we'll have good approximation and the bias will be low. If we have a very small hypothesis class, then the bias will be large. Variance tells you how much the output GD of x fluctuates around G bar of x as we change D. So for different data sets, how much does GD of x fluctuate with respect to the mean value? If the fluctuations are large, the variance will be large. If the fluctuations are small, the variance will be small. So in other words, it tells you how specific is the output with respect to the given training set. Or in other words, how much overfitting happens, right? If the output is very specific to D, then you're overfitting because now you're being very capturing just the properties of that data set. But if you are not very sensitive to D, if you are not going to have a lot of variation, then you won't be overfitting. So if you have a small h, then you will have maybe a small hypothesis class with few elements. F of x might not be in the hypothesis class, it might be outside, and your best approximation might be here. So this will be the bias. So the gap between the ground truth and your best approximation in the hypothesis class is going to be big. But because the volume of this is small, the fluctuations won't be that high. So the variance will be small. So if you have a small hypothesis class, you will have a large bias, but small variance. Okay. On the other hand, if you have a large hypothesis class, then you will have many points. These are all candidate hypotheses. F of x might be somewhere here. So G bar might be this, the closest one. So we will be having a good approximation to F. So here you will have a small bias. But then you could change quite a bit in general. Depending on your data set, you will have many options. So you will have a large variance. So if you get a very rich, if you choose a very rich hypothesis class, you will be able to have a good approximation on average. So your bias will be small, but then your variance will end up becoming larger, and so you may end up overfitting. And what we know is that bias plus variance equals the test error. So if your bias is large, it's not good for the test error because you're essentially underfitting. If your variance is large, it's also not good because you're overfitting. What matters is the sum of the two. So an ideal hypothesis class will be one where the sum of the bias and variance is small. No questions? It's all clear? Okay, good. So what we will do is we'll prove that in the general case. We will show that if we define bias of x as g bar of x minus f of x square and the variance of x as expected value over d, gd of x minus f of minus g bar of x square there and delta of x as expected value over d of gd of x minus f of x square. These are the three quantities that we defined. Then delta of x is the bias of x plus the variance of x. This holds in general, not just for the example we have. And the way to do that is to start with the left hand side, LHS. We are computing the expected value of this quantity, gd of x minus f of x square, right? So let us expand it. We'll write it as gd of x square plus f, or actually let me do it slightly differently. So I have gd of x, I will subtract g bar of x and add g bar of x and then keep f of x as it was. So I will use this expression, just adding and subtracting the same quantity. Let's call this A and this B. Then I have expected value of B of A square plus B square plus 2AB. Okay, it's A plus B square, so I have A square plus B square plus 2AB. This is expected value of D. What is A? A is GD of X minus G bar of X square plus the second quantity B, which is G bar of X minus F of X square plus 2 times GD of X minus G bar of X, G bar of X minus F of X. Okay, just substituting for A and B. All right, so let's look at this term by term. What is the expectation of D of this term? Does this look familiar? What is it? It's the variance. What is the expected value of B of the second term? G bar of X minus F of X squared. So the first thing is that this does not depend on D. Data set. So it's a constant. It's just G bar of X minus F of X squared. What is that? Does this look familiar? Anything here that matches? Is the bias? How would you simplify the last term? You have 2 GD of X minus G bar of X times G bar of X minus F of X. And you want to take the expectation with respect to D. How would you simplify that?
So the last term is the bias.
Well, it's the square is the bias technically. So, but what can you say about this term? It's a constant with respect to D, right? So you can take 2 times this term outside the expectation. And what you are left with is the expected value of this quantity. Expected, you can put ED here of GD of X minus G bar of X. What is that? That's 0. So the last term, when you take the expectation, actually gives you 0. So that's just the proof for the general case. So what we have shown is that delta of X is the bias of X plus the variance of X at each X. Now this looks good, but there is a small difference between how we define delta of X and how we define the test error originally. In our original setup, we would fix D, we would get an output, and then we would take the expectation with respect to X, not G. G would be fixed. So our definition for test error is given the function GD for one training set D, we would compute GD of X minus F of X square. This was a squared error. This was our error at X. But then we would take the integral with respect to Px dx. So the idea was that our new query point is sampled from the same distribution as the training set, so the same Px, and we average with respect to X. This is how we define the test error. This is our definition for E out of GD. This was our previous definition. Now we are defining delta of X differently. We are again taking the same function. So should make all of this capital X because okay, because x can be vector in general. GD of x minus f of x, the same loss, square it, but then we integrate with respect to PD. We are varying the test here. We are fixing x and we are varying the options for our training data set, right? Like the different lines that we could draw and take the average with respect to those lines. So there's a slight discrepancy between the two. In the definition for the test error, we were fixing the output hypothesis and averaging with respect to the query points during the test phase. In delta of x, we are fixing x and we are averaging with respect to d. So the way to resolve this is to note the following. E out of GD is random because D is random. D is selected from PD. So it's not very meaningful to talk about the test error for one output hypothesis, because that's going to be a random quantity. Depending on which training set I get, I will get some value for the test error. To know how good a hypothesis class is, whether it is overfitting or underfitting, what I will do is I will define average test error with respect to our training set D. So what I will do is I will define E bar of out, which is the expected value of D of E out of GD. So I compute the test error and I take the expectation of E out of GD. Now E out of GD is just the expectation with respect to x. What's going on? Guys, it's time to get a break. ED of the expected value. So let me write it on the board. So it's ED of expected value of x of GD of x minus f of x squared. Okay, this is what it is. E bar of out. Now I can interchange the expectation. So I take the expectation with respect to x first, and then take the expectation of GD of x minus f of x with respect to d. And this is nothing but delta of x. So this is equal to E of x of delta of x. And delta of x is the bias plus the variance. So it's E of x of bias plus E of x of the variance of x. So the test error, the average test error that we are interested in is obtained by taking the bias of x and then taking the expectation with respect to x plus the variance of x and taking the expectation with respect to x. So it still works out when you add the expectation with respect to x. So let's take a 10-minute break and we'll continue after that.